The design of any RCC building is nowadays done with the use of STAD Pro. This STAD Pro result is very good, even if the building is so complex in nature. But checking a little with the usual method may be good in selected places where the engineer feels it doubtful. So for that, we used to calculate the uniformly distributed load over the beams in all the floors and the load transferred to the column. These things we can calculate easily, as I have said in my previous videos. But in this video, we are going to see how the bending moment in a column is arrived due to the vertical load on the beams and slabs. The calculation of bending moment in the column is more important because the columns which bears the beam of long span will generally receive or will generally suffers a higher level of bending moment in the column. That bending moment direction is also required to be known for designing the columns and keeping the column orientation in a correct way. In this video, I am giving you a small lecture how to calculate the bending moment in the column with the use of moment distribution method. That moment distribution method is more accurate. This can be done easily if we feed all the data in Excel sheet, Microsoft Excel sheet, and feed all the formulas in Excel formulas. Then we shall get the result very easily. If we design if you design one calculation in a Excel sheet, the same calculation can be used for any number of times by changing the column width, depth, and the span and the load. If you change these things, the number of calculation which we are going to do in the next will be done by the Excel by itself, and the result will be given by the Excel readily. So primarily understand how to do this method of finding the column bending moment using the moment distribution method.
The drawing or sketch of a four-storied building frame. This is one column. This is one column, central column, last column. This is ground floor plinth beam. This is first floor plinth beam, second floor plinth beam, second floor floor slab, floor beam. Similarly, the third floor beam, fourth floor beam. Now we cannot calculate all the things at a simultaneously. So we are going to take this one floor only. Take this portion within the red line. From that we can calculate the column bending moment. That column bending moment is almost equal throughout the length of the column. So now we are going to calculate for the first floor slab or first floor beam and the adjoining columns. So this is the portion shown red color in the previous drawing. The joint, the left side joint, I have given the name as A, the center joint as B, the last joint as C. So this is ground floor column, this is upper floor column, first floor column. So likewise everything. The ground floor end is termed as A1, the first floor end is termed as A2, likewise B1, B2, C1, C2. This is the names given to the joints or end of the columns. Then the data available with us is the span of this first span is 6.4 meter, next span is 3.35 meter. This column upper floor height is 3.15 meter, the lower floor column is 3.75 meter. This is joint to joint distance. Actually, this must be a joint to joint distance. So this is the available names and the measurements of the individuals. Next, we are going to calculate certain things before going to calculation method. This is a statement showing for the joint A. Joint A, as we said in the previous sketch. This is joint A related things only we are seeing. In joint A, there is a beam AB, that is horizontal beam, A side to B side, this is horizontal beam. This is A1, A1 is the column of ground floor, A2 is the column of first floor. These are the measurements of the column size. 230 mm column width, 450 mm column depth, the length of the column is 3.75. That's the beam. Beam width, beam depth, beam length or span. Similarly, the upper floor. These measurements are given here. This is nothing but the same measurement converted into meter. From this, we are going to calculate one item called moment of inertia of the beam or the column. That formula is I equal to BD cube by 12. BD cube by 12. So the breadth we know already, this is 230 mm, depth is 450 mm. From these two, by 12 is giving this result. This calculation is here, 0.23 into 0.45 into 0.45, 0.45 by 12 is this much. This is called moment of inertia of the section. Likewise, the same is calculated for beam. This can also be the same because the section size is same as the column. The ground floor also the moment of inertia is the same. Next we are coming to another item called stiffness factor. Stiffness factor formula is K equal to 4I by L. I means nothing but the same thing as we found in the previous calculation. So feed this I, that is the I is 0.00174, here it is. The length by L is 3.75 is here. 3.75 is 3.75 into 4, this value comes as this much. This is called stiffness factor. Similarly, do the same thing for the beam and the upper floor column. These things will differ because the length are different for each things. So these things are different, but approximately in the 0.00 or next. Another item we are going to call it as distribution factor. This is the factor which is most required for calculating the column bending moment. This item we are going to feed in the next statement. This formula is nothing but the K value. Previously calculated value is called K value. K value of this span, this upper floor column, divided by K value of all the floors, all the beams. The column upper floor column plus K value of the span plus K value of the upper floor column is this thing. These things are here. The same thing is here. This, on calculating these things, we are getting this value 0.360177, which is called the distribution factor, which is more important for the next calculation. In addition to this, we are also calculating another one thing, which is called the fixed end moment of the beam. We are considering only about the beam, not about the column, because there is no horizontal load on the column. So there is the bending moment. As per theory, the bending moment comes only in the beam. That value is calculated by fixed end moment is WL square by 12. This is the formula. On W is nothing but the uniformly distributed load. Uniformly distributed load means, as I said previously, in the usual calculation of finding the column axial load or bending moment in the beams, this uniformly distributed is more important. That we have already calculated in the previous sessions. And the length is available. This is 6.4 meter for the beam is concerned. We are filling this L as 6.4 meter, W as 36.09. Divided by 12, this value comes as this much. This is bending moment. This is kilonewton meter. For this calculation we have done is for joint A only. Similarly, we are calculating the same thing for joint B. Here also we are finding the same distribution factor. And here we are finding the bending moment. Here there are two beams, horizontal beams, one on the left side of the beam, in another on the right side of the beam. See here, This is a B, left side one span, right side one span, upper above column, lower column. These things are required to be noted. As far the B is concerned, we are having four members: span 1, span 2, upper floor column, lower floor column. For these things, we are finding the distribution factor and the fixed bending moment in the both the spans. For the both the span 1, this form the same formula, the value is this much. Okay. Next we are coming to joint C. Joint C is also the same type. We should calculate all these things for joint C. Here there are three members, one span, two column members. For this we are calculating this distribution factors noted here. Please note all the adding all the distribution factors, that the total will be 1 only in every place. This should come as 1. If it is not coming as 1, then the calculation must be mistake somewhere. You make sure of these things. Then the fixed end moment in the same beam, this WL square by 12, calculate these things based on the uniformly distributed load. So after finding these things, we are going to the main calculation sheet for finding the bending moment in the column. This is the calculation sheet for finding the bending moment in the column. This calculation is made for two spans and three rows of column. The yellow lines, the line 1, 1, line 2, line 3, and also line 4 pixel. These things we have already calculated in the previous calculations for joint A, joint B, joint C. Those things I have brought here. This is members for A joint. There are three members called A1, A2, and the beam AB. In the joint B, there are two beams called BA and BC, and two columns that is going to ground floor and going to first floor. And similarly, in C, there are three members, two columns and one beam. Okay. The third line is distribution factor. We have already calculated in the joint A, the last line we found. The first line is 0.36, then 0.42, 0.22. Similarly, for B, C, and these things, I have written from previous calculations. Then fixed moment also we saw in every joint in the bottom line, we saw this is as 123.19 kilonewton meter. This the right side, the same bending moment will come in BA. This will be with a different sign. 123.19 is the fixed moment here. Similarly, BC and CB. These are the fixed moments we calculated in the previous sheet. I have filled up these things. As far as the columns are concerned, the bending moment in the column can only be 0 initially because there is no horizontal load in the beam, because the column is vertical, so there must be a load in the horizontal direction, then only a bending moment will come. As there is no load in the horizontal direction, the bending moment must be taken as 0 as far as the columns are concerned. See, all the column bending moments have I have written as 0. Okay, next we are coming to calculation. First calculation, first line, we are using this unbalanced moment. How to calculate the unbalanced moment? Add the three moments in the same joint. That is called unbalanced moment. 0 plus 0 plus 123.19 is this much. As far as B is concerned, minus 123.19 plus 0 plus 0 plus 33.75 is this much. Similarly for C, you write with sign. The sign is more important. Without forgetting the sign, you put the sign there. Next line, we are calculating, we are distributing the common bending moment or unbalanced bending moment in the joint in the proportion of the distribution factor or the distribution proportion. This may also be called as distribution proportion. Multiply this one with the proportion factor or distribution factor, then put here with change of sign. Here is 123.19 plus. We put here as minus by multiplying these two. Similarly, do the same thing, the total bending moment into the proportion factor or distribution factor, put here with change of sign. Similarly, in all joints, do this. Okay. After putting this, we are finding, we are obtaining the values in all the members, AA1, AA2, AB column, AB beam, BA beam, everything. We are finding this in every place. See here. Okay. Next, we are going to carry over these things to another nearby joint. In AB, there is a moment of 25.99 by 2 is to be put here in the B side without changing the sign. Without changing the sign. Let us, the B side, the moment is 13.45 by 2 is 6.725 without changing the sign put here. Similarly, in this joint, this between the joint B and C put here. So this is one cycle is completed for the balancing bending, balancing the moment, distributing and carrying over. The same cycle is to be done for 4 times or 5 times. See here, this is the bending moment finally available in the joint A and joint B. The totally this is here, this is 0, this is 0, this is 0. So all the 3 add put here, that is to be distributed and carried over. Similarly, do it for 4 times or 5 times till we are receiving a unbalanced moment of unbalanced power near to 0. This is almost near to 0. So if you get a near to 0 value, then you stop doing this distribution. Now take a total. From the place of distribution, 44.36 minus, add these columns and we are getting this value. Similarly, do this for this portion, this value we are getting. It means what? The total for minus 47.07 kilonewton meter is the bending moment in AA1 column. Similarly, 56.04 minus is the bending moment in column AA2. Similarly, this much. So by this way, we are finding the bending moment in column and beams final. The beam bending moment also, the actual bending moment working will be 103.12 only. Actually, the theoretical moment is this much. This is not actually acting on the beam. This we are finding. This is the final bending moment we are finding in the column and beam. These things I have made in Excel sheet. This is the Excel sheet. Moment distribution of a frame for a column. Here I have calculated these things. What is the uniformly distributed load, length of the upper column, length of the lower column, span length, span width, and the beam width, beam depth, column length, etc. I have put these things. This is as far as A joint A is concerned. This is the measurement. The same thing. The measurements I have written in this colored places. I have written. But see, you can find here it has been written in formula bar, Excel formula bar. The same thing as we saw previously, measurements in meter, then see a sample calculation for the first reading, then this is moment of inertia, then k value, then the beta value, distribution factor. These things we have calculated here, and the bending moment is also calculated here. These things I have fed in formula bar. See here, this it is possible for you to see in the YouTube. Please see. Otherwise, please see what is the formula bar in the laptop. That will be more useful to you. Similarly, I have made the same calculation for B, joint B, for joint C. I have made the calculation, and these calculations results I have brought to this moment distribution tabulation. These values I have brought to this cell through formula bar. That is these things. So these are calculations. The addition of these things is here. These are also calculation. This total bending moment is multiplied by this distribution factor and put here. Similarly, I have done everything only in formula Excel formula bar. If we change any measurement, any length or any span, automatically the result will automatically get changed. By this way, we can find the bending moment of column at any place within 1 minute or 2 minutes by changing the dimensions. Okay, this is a. I think this video will be more helpful to you for finding the column bending moment. Uh, Please share this video to your friends, the engineer friends or architect friends somewhere, and subscribe this video. I am going to post next. I am going to post how to design a isolated footing, and next I am going to post a strip wrapped footing, and next all types of foundations I am going to continue. In previous videos I have made different videos where I have give a clear clarification about finding the column axial moment, bending moment in the column, axial loads, everything. I have made a clear lecture in my previous videos. Please share, please subscribe, please like it. Thank you.